3 o'clock now. We can start. Okay, Amit, welcome to QIQT 2021. I see numbers are increasing, but somehow right now participants are just 52. Morning session, it was more than 170 anyway. So it's afternoon, maybe after lunch they are taking rest. Anyway, so it's a pleasure to introduce Amit, whom I know, I think, for quite some time. Since 2004, when he joined PRL as Junior Research Fellow. So after spending some time in PRL, along with Professor G.S. Agrawal, with whom he was doing PhD, he moved to Oklahoma State University and finished his PhD, of course, in quantum optics, theoretical quantum optics, working with Professor Agrawal. So finished his PhD with Professor Agrawal in 2011. And from there, he went to CQT, Center for Quantum Technology, National University of Singapore. And he was there for 3 years, 11 to 14. And then he joined NIT Rourkela as assistant professor. And he was there since since 2014 to November 2020. And now, presently, since December 2020 means he is in JNU as associate professor, and I think he's enjoying JNU life. Okay, I miss my JNU life. I've done my PhD there, so hope he likes JNU, present JNU. So with these, and I think theoretical quantum optics, but in general his interest presently is more into this waveguide arrays, photonic lattice, and this kind of stuff. Let's hear Amit on non-classical light in waveguide arrays or one-dimensional photonic lattice. Okay, Amit.
Good afternoon, and thank you, Professor Singh, and I also thank Professor Panigrahi and all the organizers for giving me an opportunity for a talk. So today I'm going to talk about some of my work on photonic lattices or coupled optical waveguides, which have emerged as an important quantum optical system for quantum information processing and quantum simulation. So let me share the screen. So is it visible to everyone?
Yes, sir.
Yeah. Okay, so I'm going to talk about non-classical light and then in the photonic lattices. So first of all, if you see this figure, here I have shown this two-dimensional photonic waveguides which are coupled with each other, and these waveguides can be fabricated using the femtosecond laser writing technique. So it gives a lot of flexibility to fabricate waveguides with desired properties. And this will be an important feature for our talk. So this is an outline of my talk. So I will start with the introduction. So why we are interested in optical waveguide system. So as you may be knowing, that there are many physical platforms that are being pursued for the development of quantum technologies. So for example, some people are working with IBM Q systems, which are based on superconducting qubits. Then you have trapped ions. You also have optical systems. So optical systems have some advantage. So I will discuss it in the next few slides. So using this optical system of photonic waveguides, I describe my work on the generation of multi-qubit W state. So W state is an important entangled state, which has application in quantum teleportation and quantum communication. Then I move to describe my work on perfect transfer. So here we are looking for perfectly transferring the quantum state from one side to the other. We also look at the revival of the quantum states. And then I will describe my work on optical simulation. So quantum simulation is emerging area of research, which will be using the quantum technologies that are being developed. And I will describe my work on the simulation of Majorana equation in optical waveguide lattices. And I will conclude my talk with future scope. So we are in the middle of a second quantum revolution. So the quantum technologies are going to make a very important impact on our daily life. And in India also, there is now a lot of focus on these quantum technologies. So as I said, that there are a variety of physical systems that are being studied. So each system has its advantages and disadvantages. All these systems, they use these important features such as quantum superposition, quantum entanglement, squeezing. So these features are very important as far as these quantum technologies are concerned. And however, one problem is that these features are very susceptible to decoherence. So you always have to deal with decoherence because the system is always interacting with the environment. In some systems, the decoherence is less. In some systems, the decoherence is more. But you always have to deal with decoherence. So quantum optical systems are interesting because they are less sensitive to decoherence. So decoherence effect is less in optical system, and this is one of the advantages. So as I said, that each physical platform has its advantages and disadvantages. So one of the important advantage of the quantum optical system is that the decoherence is very less. So one of the important quantum optical system is the system of optical waveguide arrays, which can be fabricated with very less decoherence. So with as you might be knowing that the technology for the fabrication of waveguides have matured a lot, and now we are told by the experimentalists that they can fabricate waveguide arrays with very, very small loss. So we focus on these integrated waveguide arrays. And so another advantage of the waveguide system, which we are using as a physical platform, is that it is scalable. So you can fabricate many waveguides, and even if the size of the system increases, the decoherence effect remains very small. They are stable. They are stable because you can fabricate them using this femtosecond laser writing technique, which fabricates waveguides inside glass. And once you fabricate it, it remains as such. You don't need to. So if you talk about the bulk optical element, then once you set up and do the experiment, and then you have to again set up, they are not stable. So optical waveguides, they can be fabricated in glass, and they can be very stable. You can keep them and then again do the experiment, and they can be fabricated precisely. So therefore, these optical waveguides have started finding applications. So the application of optical waveguides in classical physics is very well known. They are used for communication purposes and information processing. But recently, they have been finding application in generation, transfer, and revival of quantum states. So these are very important as far as quantum technologies are concerned. They are also finding application in quantum simulation. So quantum simulation is emerging area of research where you simulate difficult problems which cannot be solved using classical computers. So you use quantum simulators. So the quantum technologies that are being developed will be used for quantum simulation. And optical systems have also been finding increasing application as far as quantum simulation is concerned. So we'll describe, so we have done some work which is actually done with a group who have done the experiment also. So we have done optical simulation of Majorana equation. So I'll describe my work on optical simulation of Majorana equation. And then these things, we are focusing on optical waveguides, but one can also, our results can also be implemented in coupled cavity arrays and micro ring resonators, which are also very matured technology. So here is the model for the optical waveguide. If you see this, you have many waveguides which are placed close to each other, and they are coupled because of the evanescent overlap of the modes. And if you see this coupling between these waveguides are different. So in general, you can fabricate a structure where the coupling between the waveguides is different. And you can do that by placing these waveguides at different distances, because the coupling between the waveguide is dependent on the distance between the waveguide. So formally, if you write the Hamiltonian for the system, then this is the Hamiltonian, and AJ is the AJ and AJ dagger are the modes of the, so J is the index that we use for numbering the waveguide. So if you're talking about the first waveguide, then J is equal to 1, and so on. So, so AJ is the annihilation operator for the Jth waveguide mode, and delta J and Kj are related to the propagation constant, and Kj is the coupling constant. So both these parameters can be tuned precisely using this femtosecond laser writing technique. So you can generate a variety of Hamiltonian as per your requirement. If you consider delta J and Kj to be constant, that means you consider uniform arrays. So that means all these waveguides are identical and they are placed very close to it. They are placed at equal distance. Then you get something called uniform arrays. However, as I said, that this Kj and delta J, they can be tuned as per our requirement. So we'll use this feature for our work, which I will describe later. So these waveguides are fabricated using the femtosecond laser writing technique. And one of the important feature is that these systems can be fabricated with very low loss. So if you want to look at a review on this femtosecond laser writing technique, this is a very good review paper which discusses about the femtosecond laser writing technique. So to move further, let us first talk about how we realize qubits in these waveguides. So you must have already been introduced about this bits and qubits. So bit is just 0 and 1, and qubit can be in a superposition state. Then, as I said, that there are different physical platforms for development of quantum technologies, and therefore there are different ways to realize these qubits. So you can use the superconducting system, or you can use the trap band system. Here we are focusing on the optical system. So in optical system, the qubits are realized, they can be realized using the polarization. So you have horizontal polarization, you can call it 0. You have vertical polarization, you can call it 1. And qubits can be in superposition. So you can have the superposition of vertical and horizontal polarization. So that is the state alpha 0 plus beta 1. Then another way that we use is by looking at the presence or absence of the photon in the waveguide. So here we are showing that if there is one photon present in the waveguide, then we will call it 1, state 1. If there is no photon, then we'll call it 0. So this way you can get qubits using this waveguide mode. So this is also a way to have a single photon qubit. So note that there is no there is only one single waveguide. So we are showing that if the photon is present, then we call it 1. If the photon is not there, then we call it 0. So you don't, one can also talk about multi-qubit. So it is not necessary. If you have many waveguides, then you can talk about multi-qubit states. Instead of talking just about single qubit, you can talk about multi-qubit state if you consider more number of waveguides. And when you talk about multi-qubit state, then these multi-qubit states may be entangled. And if you consider multi-qubit state, you have a variety of entangled states. So W state is one of the important class of entangled state. So this is the form of the W state that I have shown here. And these coefficients Ci, they need not be equal. So if you talk about the symmetric W state, then all Ci's are equal, but they need not be equal. So this is a general form of the W state. So as I said, the symmetric W state have all the coefficients equal to each other, and therefore you get 1 by √3 factor. So this is a symmetric or a symmetric W state. One can also consider perfect W state, which has unequal coefficients. So 1 by 2, 1 by 2, and 1 by √2. And this perfect W state is useful for perfect teleportation. So the question is how to realize this perfect W state in optical waveguide system. So here is our scheme. We started with a separable state. So in particular, we start with a single photon in the middle waveguide. So we have shown here there is single photon in the middle waveguide. And then we propagate it. And as we propagate it, we expect to generate a perfect W state. So note that these waveguides are non-uniformly coupled. So they are identical. I have shown them with the same color. So that means they are identical, but they have non-uniform coupling. So K that I had shown when I talked about the Hamiltonian for the waveguide. So K is different for all for these waveguides, and therefore they are non-uniformly coupled structures. So we did our simulation, and our aim was to generate a perfect W state. And we found that if you have a coupling, which is of this form, so the coupling between 1 and 2 is K, and the coupling between 2 and 3 is √2K, then you can generate the perfect W state. And this kind of coupling you can generate if you place these waveguides at these distances. So the distance between 1 and 2 has to be D1, and the distance between 2 and 3 has to be D1 minus K log 2. And this kind of, it is possible to fabricate such structures. As I said, that this femtosecond laser writing technique allows to fabricate structures with desired coupling. So it is possible, and we feel that this kind of arrangement can be fabricated, and therefore it should be possible to generate this perfect W state using our scheme. So here is the dependence of coupling on distance, and by tuning the distance properly, you can generate the perfect W state. So if you start with single photon in there, so here I am showing the generation of perfect W state. So if you start with the single photon in the second waveguide, at this distance, at Z equal to 1.634 centimeter, you generate the perfect W state. So you have to propagate it, to propagate the single photon to this distance, and then you will be getting the W state, perfect W state. It is also important, even though the loss in optical system is less, but it nevertheless is there. You cannot completely ignore the loss. So we have also taken into consideration the effect of loss using the master equation and solve this. And we found that, so here we are plotting the fidelity, which gives you the similarity between the density matrices with and without loss. And we find that the fidelity doesn't decreases much for the relevant values. So beta is the loss. So for the relevant values of loss, we find that the fidelity doesn't decreases much, and therefore our scheme is robust against decoherence. Now, one can also generalize this. So when you increase the number of qubits, decoherence effect becomes more and more important, and therefore it is difficult to generate multi-qubit state with a large number of modes. So here we have generalized our result and proposed the generation of multi-qubit entangled state using the waveguide system. So this is a state that we are interested in. This is a generalized perfect W state. So n can be any number. N is greater than 2, greater than or equal to 2, and it can be any number. So you can, so as long as you have reasonable amount of loss, you can generate the W state using our scheme. So here is the 4-qubit W state. And so again, we are taking these couplings to be different. And we do the calculation and find that these are the couplings that are required for the generation of this generalized perfect W state with n equal to 4. So in this scheme or in the previous schemes, we have to optimize it for every n. So if you want to generate n equal to 4 W state, then you have to do the calculation and find the coupling constant and propagation distance. So what we have done is that we have generalized our scheme. So we have considered a ring type waveguide system where these waveguides are kept on the ring, and there is a central waveguide. And then we are looking at the generation of generalized W state. And we found that if you propagate the single photon to this distance, so kz is the normalized, so k is the coupling and z is the distance that you propagate. So if you propagate this photons to this distance, then you get the generalized W state, and this is true for all n. So you can consider any value of n, and it will give you the value for the normalized propagation constant. So here is the plot. So if you want to generate, for example, n equal to 7, then you have these probabilities. So these probabilities correspond to the probability of finding the photon in each mode. And at z equal to kz equal to pi by 4 root 6, you get the desired W state, which is the W state for n equal to 7. So next question that we ask is that whether it is also possible to perfectly transfer the quantum state. So what we want is that let's say we have a single photon state or a squeezed state or any input state. We have it at the input side, and we want to transfer it to the output side. So we give the input at this side, and then we let it evolve. And this is the output side, and we want it to be perfectly transferred. So if you consider uniform arrays, then you can show that it is not possible to perfectly transfer the input state to the output side. There will be some transfer, but there will not be perfect transfer. So for this, you need this optical waveguides with this kind of coupling. So I have shown this coupling, and this coupling can again be generated using the this femtosecond laser writing technique. And this perfect state transfer is important to efficiently transfer information between the nodes, and which is important for scalable quantum computing. So here is the Hamiltonian. So this is the system that we are considering. And so as you can see that the coupling that is required is of this form. So if you have uniform coupling, then you cannot perfectly transfer the quantum state. But if you have coupling which goes like this, then it can be shown that the state will be transferred. So if you start with a single photon state, here, then you can perfectly transfer it to the other waveguide. So this, so we wanted to study that, so it is possible to transfer single photon state. So we wanted to ask the question whether it is possible to use the same system for transferring a 2-photon Fock state, a noon state, and a squeezed state, and we have also considered a coherent state. All these states are important quantum states. They are regularly produced in quantum optical laboratories, and they also have very interesting applications. So we wanted to check which of these states can be perfectly transferred. So we considered first the transfer of the average photon number. So Nj here is the average photon number, and we wanted to check whether it is possible to. So we start with the first waveguide, and we want to transfer it the light to the 20th waveguide. So first we look at the average photon number. So if you look at the average photon number for these states, we can see that there is a complete transfer. So so in all these cases, for 2-photon Fock state, 2-photon noon state, squeezed state, and coherent state, in all these cases, the average photon number is completely transferred. So next, we wanted to look at whether it is also possible to, whether the perfect transfer of quantum state is also possible or not. So for this, we have calculated the fidelity. So fidelity, this is an equation for fidelity. So if fidelity is 1, that means the state has been perfectly transferred. So we found that for the 2-photon Fock state and noon state, the fidelity was 1. So therefore, these states are perfectly transferred. So in addition to the average photon number, there is a perfect transfer of quantum states as well. However, for squeezed state and coherent state, the perfect transfer doesn't take place. So the fidelity is not equal to 1. So usually it is difficult to experimentally measure fidelity. So we look at squeezing. You have, I think you have been introduced about the squeezing. So you have reduced fluctuations in one quadrature at the expense of other. And the interesting thing is that squeezing can be measured using the homodyne detection technique. And we have defined the squeezing parameter Sj. And if this squeezing parameter is less than 0, the way we have defined, if it is less than 0, then that means there is reduced fluctuation in that mode. So in that quadrature. So here we look at the squeezing. We look at this squeezing parameter, how it varies with time. Here in plot A and B, we are looking at the squeezing and in Q and P quadrature for the input waveguide. So remember that we are giving the input in the first waveguide, and we are looking at the Q and P quadrature, the squeezing and the Q and P quadrature. So initially, the Q quadrature is squeezed, and as time progresses, it varies. And then we are looking at the squeezing in the output waveguide where we want to transfer the light. So here the output waveguide is a 20th waveguide. So you can see that the squeezing here is in the Q quadrature, but here the squeezing is in the P quadrature. So the quantum state is not getting perfectly transferred. The input state was squeezed in Q quadrature, the output state is squeezed in P quadrature. Therefore, there is no perfect transfer. So even though average photon number is getting transferred, but the state is not getting perfectly transferred. So this can be experimentally checked also by using the homodyne detection technique. So in some cases, we find that for a squeezed state also, there is perfect state transfer. So for n equal to 21, there was perfect state transfer. For coherent state also, which is classical state, there is no perfect transfer. In some cases, there is no perfect transfer of the quantum state. So we conclude that for the single photon state and path entangled states, they are perfectly transferred. However, the squeezed and coherent state, they are not always perfectly transferred. So we also looked at this another structure where we study the revival of the input state. And in this kind of system, the revival is dependent on the input waveguide. So it depends on, so the revival is not always taking place. So if you give the input in the first waveguide, so this is very interesting. in the sense that if you give the input in the first waveguide, then there is revival. But if you give an input in other waveguide, then there is no revival. So this kind of waveguides have been studied. So here we are again plotting the squeezing parameter, and you can see that these nice revivals. If you give the input in the first waveguide, if you give the input in the last waveguide, then these revivals are not complete. So you can also look at the revivals for this path entangled state. So here we are showing path entangled state where the photons are both the photons are coupled to the same waveguide. And in this state, this is we call this as anti-correlated path entangled state. So in this case, the photons are always coupled to different waveguides. We consider these two states, and we look at this correlation function, which gives the probability of finding one photon at jth waveguide and another photon at kth waveguide. So here are the results. So here also we consider a small number of waveguides, and again you can see that there is, if you give the input to the first three waveguide, then there is revival of the input state for the correlated state. Again, for the anti-correlated state also there is a revival. So at t equal to 0, you have this state, and at t equal to 6.9, again you have this same state. So there is revival in both these cases. And so if you consider a large number of waveguides, then you don't see the revival, then you see this very different kind of correlations. And the important thing is that if you look at t equal to 1, then you see that these photons are always anti-balanced. So if one is found at 20th, then the other one is found at 40th. So they are never together. If you look at this case, which is the case for the anti-correlated state, then the photons are always found together at t equal to 1. So up to now, I have discussed the application of waveguides in generation and transfer and revival of the quantum states. So now I describe my work on the simulation of equation of a Majorana equation. So this is the Majorana equation. It was written by Majorana for describing Majorana fermions. So Majorana fermions are neutral and they are their own antiparticles. And if you see this equation, most of the time you'll see another equation which is written as psi equal to psi c. So that is for Majorana fermions, and these Majorana fermions have found a lot of applications in quantum information processing, and they have also been shown to be important as far as condensed matter physics is concerned. So this Majorana equation was written by Majorana, and if you have a charged particle, then the second term in this equation implies a continuous conversion of electric charge, and therefore it becomes unphysical. And you can not write it in the Hamiltonian form, and therefore you cannot directly simulate it. So this is a fundamental problem. This is not a problem with the system. This is a fundamental problem. You cannot simulate this equation in any physical system. It's not that you cannot simulate it in an optical system. You can simulate it in trap dance. There is a fundamental problem with this equation that you cannot simulate it in any physical system. So because of the presence of this psi c. In 1 plus 1 dimensional space-time, the Majorana equation reads as this. So same equation, but written in 1 plus 1 dimension. And then again, you see that there is this complex conjugation operator, and this equation cannot be simulated in any physical system because of the presence of this complex conjugation. And therefore, the Hamiltonian formalism is impossible. So so quantum simulation or optical simulation is where if you cannot simulate something in any physical system, and then you look at the artificial systems and try to simulate it in those systems. So here we look at, so what we do here is that we break this equation in two parts. So what we do is we write psi as psi plus and plus I psi minus. And when you do this, then this equation becomes uncoupled. And this equation now is in the form of the Dirac equation. And Dirac equation is a physical equation which has been simulated in many systems. So it has been simulated in IBM Q system. It has also been simulated in trapped ion system. So one can simulate it. One can simulate this Dirac equation. So what we do is that we have these two Dirac equation, and Dirac equation we simulate it in optical waveguide arrays. And so we have to simulate two Dirac equations, and eventually we have to get this psi. So what we do is that we consider 1 plus 1 dimensional photonic lattice, which I will show here. So this is the actual platform. So we have collaborated for this work with Professor Alex Zemite, who is in University of Rostock, and they created this very complicated and very difficult structure using the femtosecond laser writing technique. And so you see that there are two sets of these waveguides, and you separately excite them, and then you collect them, and then you measure the psi that I said. So you simulate psi plus and psi minus separately, and then you do this operation of psi equal to psi plus plus I psi minus. So this structure is very complicated structure, and this shows the power of this femtosecond laser writing technique, that you can generate this kind of structures using this technique. So this work they fabricated. We proposed them, and they fabricated this structure, and we were able to simulate the Majorana equation, which is unphysical equation, and we were able to. So basically, we measured the intensity, and through the intensity pattern, we were able to find out this psi. And so this work was also highlighted in Optics and Photonic News. So I will like to thank all the people who have been who have contributed to this work, and I have been collaborating with them, and our students also. So to conclude, these waveguides are finding interesting applications in quantum state generation, perfect state transfer, and revival of quantum states. In addition to that, there are a lot of work that are being done for the optical simulation or quantum simulation. So it is generally believed that optical systems are not good for quantum computation, but recently these things are changing, and I feel that the optical systems are also going to play. So they already play a very important role in quantum communication, quantum metrology, but they are also going to play a very important role in quantum simulation as well. So with this, I will like to conclude my talk, and I would like to thank you again for listening. And if there are any questions, then you can ask me.
Thank you, Amit. You finished quite fast. We have enough time for discussion.
Okay, so, I was thinking I was late, so I just...
No, not late. It's minimum 1 hour. Half an hour was discussion. You finish in 45 minutes. Less than 45 minutes. 40 minutes.
I tried to be fast.
No problem. So we have more time for discussion. Let's see. I don't see any question in the chat box, but people who are interested in asking questions, students and others, they can unmute themselves and ask questions. You are free to ask questions. Anyone want to ask question? Please unmute and ask. Hello.
Afi, can I ask a question?
Oh, sure. Why not?
See, Amit.
Yes.
So this Majorana state which you created, that is actually bosonic, right?
Yeah.
So does it carry any topological information? Like, for example, typically Majorana states in principle can be robust. Namely, how does it behave with respect to noise?
Yeah, we have not checked. It will be interesting to check. We have not checked that.
Because this is a superposition.
Yeah.
It could be possible that it will be robust against decoherence and other kind of noise also.
Yeah.
Now, what kind of angular momentum does it carry?
So we are talking about 1 + 1 dimensional space-time.
I agree, yeah. But psi plus I psi minus, no, right?
Yeah.
So if psi plus is like linear polarization, then this could be having some angular momentum, no?
Psi and so these are amplitude. So what we are doing is that we are looking at when they did this experiment, they actually worked with classical light. So they made psi plus and psi minus. These are amplitudes of the field. So they are measuring the intensity, the resultant. So they are combining this. They are combining these two amplitudes, and then they are measuring the intensities. So that correspond to mod of psi square.
Okay, we have got 2 questions in chat box. One question is, since a photon is a boson, there is a possibility of multiple photons that can occupy a state. So in a Fock state, as described in your presentation, so in a Fock state, how can we control the occupancy number as to include only 1 photon?
So it is possible to generate these Fock states. So there are so if you consider n equal to 1, then you have single photon state. So there are many sources. You can use the spontaneous. I think there is already some discussion. You can use the spontaneous parametric down conversion process, where you generate one photon and then you detect 1 photon, and then you are sure that you have 1 photon in the other mode. So similarly, you can also detect, you can also have sources for 2 photons.
Okay, I think that answers the question. And other question is from Akshay Kumar. How does the photons interact non-linearity within the waveguides? Okay, so within the waveguides, what basic concept is utilized in that?
So here they are interacting because they are placed close to each other. So there is so their evanescent modes, they overlap, and because of that there is coupling. So there is if you couple a photon in one waveguide, there is a finite possibility that this photon can hop to the other waveguide, which is placed close to each other because of this evanescent coupling. Yeah, so that's how they are. That's how
it's not the non-linearity. It's not the non-linear effect. It's a one-instant wave coupling, basically.
Yeah, non-linearity is if you work with if you are working with these waveguides and you are working at high intensity, then non-linear effects will also come into play. So then then we have to account for the non-linear effects as well.
But we are working with single photons.
Yeah. So we are working with single photons, so that is not possible. If we work with classical light, and then there is a possibility of nonlinear interaction.
Okay. Any other question? So, Amit, you studied this noon state as well as single photon state and squeeze state.
Yeah.
Only for squeeze state there was no perfect transfer.
No, actually for coherent state also.
Coherent state also.
Yeah.
Then you told N20 there was no perfect transfer. The moment you make it N21, it is perfect transfer.
Yeah. So
why this kind of thing? Can you explain?
So what we have done is that both this squeezed state and coherent state, we can expand it in the Fock state basis. And so what we have done is that we have expanded it in the Fock state basis, and then we have looked at the evolution of all these components. So Cat0, Cat1, Cat2, Cat3, all these components. So in when n is equal to 21, then all these. So if you see Cat n, it evolves differently. For every value of n, it will evolve differently. So if you have a beam splitter and you give an input, for example, then the Cat n will evolve differently. It will acquire different phase. So all these components, they acquire different phase, and when all these phases are equal, then there is a global phase, and then there is a complete recovery of the quantum state. But when these phases are different, then there is no global phase, and then that's why this quantum state that we get is different from the input state.
Okay. So there is question from Narsimha.
Yeah.
He is asking photon helicity and polarization. What is the difference?
So here we are not considering that, but they are different concepts. I think both can be used as qubits, I guess. So polarization, I have already shown that it can be used as qubit. So polarization is related to the direction of the electric field, and yeah, so that I think that is the difference.
Okay. Then another question from Subimal Devo. Subimal is asking question. How robust is the perfect transfer with respect to fabrication issues, such as fluctuations in the waveguide spacing?
Yeah, so they are able to fabricate very precisely when so if I remember correctly, so when we were working on this experimental simulation of this Majorana state, then I have seen in that work that they are able to fabricate these structures very precisely. So it's if you talk about the fluctuations in this fabrication, then it's of the order of 10 to the power minus 3 or 10 to the power minus 4. So if you talk about the fluctuations in coupling, it will be of the order of 10 to the power minus 4, I think, or 10 to the power minus 3. So I don't think that it is a problem. So there has been some experiment on perfect transfer of this entangled states that was recently done. So that is not a problem. They are able to fabricate it very precisely. What we were interested in is looking at the possibility that whether one can transfer other states like squeezed state and coherent states. But I think that a single photon state and noon state, they can be easily, one can fabricate structures with very precisely.
Okay. Subimal, you have more questions? Subimal? I think he can only type, he can't listen anyway. So, any other question?
Yeah, hello.
Hello, Subimal,
Yeah.
you can ask more questions. Why don't you ask?
Thank you.
Long time.
So the number, the 10 to the power minus 3 or 10 to the power minus 4 that you mentioned, that tolerance is a relative tolerance. You mean, right?
Yeah, so you calculate, so if you say del, we were denoting del, this propagation constant by delta J. So if you calculate delta J by the fluctuation in delta J divided by the actual value of delta J. So that is
relative fluctuation. Yeah, so then it's a very, very small number.
Yes, and that is a good thing about this technique. So they are able to fabricate these structures very precisely.
Okay, thanks, Amit.
Okay, Amit. I think we don't
Amit, I have a question. Although I am a co-author, but this kind of tunneling, n minus root j n minus 1, how practical it is?
Root J, they are able to do it. They are able to precisely fabricate structures by keeping them at the desired distance. So if you look at this slide, then if you put them at those distances, so there was the distance was dependent on log of D. So if you can fabricate it at those distances, then it is possible. And actually, experimentally, they are able to do it using this technique.
Thank you.
Amit, what was the substrate for designing these waveguides? Like, which are the material, substrate and material in which these waveguides were made? Can you?
Glass. They are fabricating it in glass usually.
Glass was the substrate, or glass was the material also? Generally, they take a substrate, over that they deposit some material, and in that material they make the waveguide. So can you tell me about more precisely about the system?
So what they so that is one method, but what they tell us that they are fabricating in glass by focusing these lasers at different. They are keeping them at different distances, and they are able to fabricate this in glass itself. That's what I.
Okay, so they have all the experimental details that they have published paper. It is.
Yes.
Okay.
Yeah. So what after discussing with them, what I learned is that they are fabricating in glass itself, and how they fabricate is that they put these lasers at different distances. And that's how they are able to fabricate. So in the first page, I showed this two-dimensional geometry. So that also they are able to fabricate by putting these lasers at different distances from this glass material.
Okay.
So I think you know more than me.
I will look into the paper. Yeah. I will look. Okay, Amit, that's, I think, I don't see more questions.
I have one more question.
Okay, sure.
Okay. So the configuration that you have studied, what you showed is you have looked at the nearest neighbor coupling.
Yes.
Yeah, this is just out of curiosity I'm asking, because there have been coupled waveguide systems where people have studied the next nearest neighbor coupling also. Is it that just deliberately it has been kept out to keep the system manageable, or it's something that can be studied or should be studied?
So one reason is that if you compare the first order and the second order coupling, first order coupling will always be more because it depends on the distance. So the distance between neighboring waveguides is always going to be less. So therefore, the first order coupling will always be more. And in these systems, the second order coupling is usually negligible in comparison to the first order. There will be a second order coupling, but it will be negligible in comparison to the first order coupling.
Yeah, so it's deliberately ignored because it will not be very significant.
Yeah. Usually it is small, but if you want to introduce this, there are ways to introduce this next nearest neighbor coupling. But usually it is very small in comparison to the first order coupling. So they ignore it.
Yeah, one of the ways is to make a non-planar configuration.
Yeah.
Okay, thank you.
Okay, so Vimal, I think we had a very good discussion, and Amit, you have given very clear presentation, very precise. So thank you for that. And with this, we conclude this talk. And we have talk at 4 itself. Next talk.
Thank you.
We are in time, yeah. Thank you, Amit.
Thank you, Amit, and thank you, RPG.
Thank
you, Prashantji. See you.
Sure. Good afternoon, Professor Suter. Are you in?
Well, good afternoon. Yes, I'm here.
Hello.
Yeah, Chiranjeev, you are in, no?
Yeah, I'm there. Leaving tomorrow.
Yeah, I know. How are you going? Fine.
Flight to Lucknow and then vehicle. 5-hour journey. Unlike Kanpur, which is 2-hour journey. Things are better in UP now. Huh?
Yes.
How, Professor Suter, how are things in Germany now?
Pretty relaxed. With the cases have been going down by almost 2 orders of magnitude, so we are now in the single-digit incidence.
But people have still, they have to wear masks when they go outside?
Yeah, in public places, inside. I mean, not in, say, in the streets, but in shops and so on.
Shops
and public transportation, yes. And I mean, the good thing is mostly that immunization is proceeding. We are now 55% roughly have received the first
Oh, that is
shot.
a very large percent, yes.
Yeah, we just overtook the United States. We've been jealous of the US for a long time.
Yeah, 55% of your population is like 5% of our population.
Yes. But we don't have a Serum Institute. I mean, India has the biggest maker of vaccines in the world, right?
Yes, it's true. But the population is also biggest.
Sure, yes.
So we have, I think, 5% vaccinated now. So.
Yeah. Mm-hmm. Well, I mean, there were some people from India who told me that probably India has already reached herd immunization because
herd immunization, yes.
Already had the virus. So natural immunization.
Yeah, natural immunity might have developed. But they say that 30% of the people might have got. There was a report. 30% of the population might have got natural immunity. So.
Yeah, and it seems that natural immunization alone is not sufficient.
Yeah.
I mean, there is this city in Brazil where apparently like 70% of the population already has caught the virus, but they're still getting new cases because the variants, the natural immunization does not protect against variants. And I mean, that may be what happened in India also, because the second wave was driven by a variant of the virus.
Yeah, variant. And more people, significant amount of people died. Close to 400,000 people died.
Yeah, that's terrible.
That's the official figure. The unofficial figure could be larger.
Yeah, but I'm still hoping that we'll get over that in a few months or so. And we're starting to travel again, say in Germany, because most people, I mean, the 55% includes also the kids, which won't get shots in the near future and may not need them. So say most people whom we need now have received 1 or 2 vaccinations already. So we can start to live more normally.
Should we start?
So shall we start, Prashant? Huh?
Yeah, we can.
Okay. So yeah, welcome everybody to this second session of the afternoon. We are very honored to have Professor Dieter Suter, who was one of the pioneers of this field, especially in experiments working on NMR and ODMR and those kind of things, ESR. So Professor Suter was born in Switzerland, and he did his PhD, both his diploma and his PhD from ETH Zurich. And then he finished his PhD in the year 1985. Then he did a postdoc from 86 to 88 in Lawrence Berkeley Laboratory in USA, in Berkeley University. And subsequently he did a postdoc he was a postdoc from 1988 to 95 in ETH Zurich. And then he did a habilitation there in the year 1993, which is like a second PhD, which people in Germany generally do. And he became a full professor, which is C4 professor in the Technical University Dortmund in the year 1995. And he has been there in the same position since that day, and he was dean of his department from 1997 to 1999. So among the many accolades, Professor Suter is in the editorial board of Journal of Magnetic Resonance, and he also has a guest professorship at University of Science and Technology in China, and also he was a William Evans Fellow at University of Otago in Dunedin, New Zealand in 2015, and he is an ISMAR Fellow also. So without further ado, I would hand over the floor to Professor Suter. Professor Suter.
Well, thank you. Let me share my screen. All right. I hope you can see it.
Yes.
Okay. Yeah, so thanks for the invitation. It's a pleasure to participate in this event. It's not quite the same as being there, but probably the next best thing anyway. Yeah, so what I would like to discuss today is how we can use spins in a specific setting for quantum information processing. And I would also like to mention I'm at TU Dortmund, but since a few months, I also have an affiliation with IISR Pune. So I guess everybody knows IISR Pune, but maybe not everybody knows Dortmund. So let me briefly introduce Dortmund. This is a map of Europe, and you see here Germany. And Dortmund is sort of in the middle of Germany, somewhat to the west. And you see here an aerial view of the campus with the main building, which is the Mass Tower. And let me also introduce the people with whom I'm working on this project and who did most of the work that I'm going to talk about. These are all postdocs, or present or former postdocs. Jingfu Zhang is from China, and the other three are from India. Koti is now a professor near Delhi, and Swati is still with me. Tanmoy is doing another postdoc in Belgium. So all these four people work on the Diamond and V Center, which you see here, and which is one of the more important systems with which we work. I will introduce it in a moment. Just let me mention also the other system which we have recently started to work with. That's the Silicon Vacancy Center in silicon carbide. And there's another Indian postdoc working on that system. That's Harpreet Singh. And if we compare the two systems, they are quite similar in some respects. I mean, silicon carbide has almost the same structure as diamond, except you have two different types of atoms, namely silicon and carbon. And it is because of this difference, however, that you have many more structures. They are called polytypes in silicon carbide, depending on the stacking of the different layers. You can have slight variations in the material, and there are more than 200 polytypes known. And in each of those polytypes, you have different spin centers, like this silicon vacancy. You can have carbon vacancies or divacancies or whatever. And one reason why this material is being studied more intensively recently is that some of these centers emit photons into telecom wavelengths. So if you want to interface these quantum systems for quantum communication, and if you want to connect them, silicon carbide may offer a bigger potential than, for instance, the nitrogen vacancy center. So the whole context of this, and of course of this conference, is the context of quantum systems, quantum computing, quantum information processing. And probably all of you have seen this paper 2 years ago, which claimed to be the first case where a quantum computer was more powerful than a classical computer. And I know there's quite a lot of debate about that, whether that's true or not, and if it was really the first or not. I definitely won't go into that. It just shows that this is really a field which is capturing a lot of attention. So I'm aware this is not the first talk that you hear on quantum information processing, but I still want to put my work a little bit in the context of that and briefly start with the basics. So what limits the power of a computer? Well, the answer to that question depends on which side of this border you are. On the left, we have the quantum world. On the right, we have the classical world. And if we cross this border, we can get quite a different behavior. And this is exemplified very well if you look at computational efficiency or at the execution time of a certain algorithm. If we want to find the so-called square-free part of a number, here in this example, the square-free part of 175 is 7, while 25 is the square part. Then the execution time of the best known classical algorithm scales like this blue curve here with the number of digits in the input. That's almost exponential. Now, you can get better or more efficient algorithms if you cross the border into the quantum world. And these are two different quantum algorithms, the Shor algorithm, which just factorizes the number, or the Gauss algorithm, which explicitly goes for the square-free part. And you see they scale differently. But how much is that different? Why does it matter? Well, the classical algorithm is classified as inefficient, while the quantum algorithms are classified as efficient. But what makes the difference? I mean, obviously the classical takes more time than the quantum algorithms, but we know that depends on the computer that you use. If you use a supercomputer, you can do it in less time than if you use a laptop. So if you take a faster computer, the curve shifts. But how much does it shift? Well, we have had progress in the last decades. For instance, in the last roughly 30 years, computers have become maybe 3 orders of magnitude faster. 3 orders of magnitude on that scale does not make a huge difference. You see the two blue curves are hard to distinguish. And even if you are much more optimistic and assume that there will be much more progress in the future and computers will get faster by, say, 20 orders of magnitude. It's hard to imagine how that will happen, but you see there's still a crossover, and for large inputs, the quantum algorithms are more efficient. And that's why there is so much research, because this difference between a second and 14 billion years is very important. So quantum computers can be much more efficient for some problems. Now, how does quantum computing work? Obviously, we need a quantum register. And at this point, I would like to briefly interrupt and check how much the audience already knows about quantum information processing. And I would like to ask the organizers to put up the first quiz. That should be available in Zoom.
Yeah, the organizers are putting it up. Just a minute.
So we are putting a question for slide number 29, right?
I think so, yes.
Yeah. So we are launching the poll. It will be open for 45 seconds. Please answer.
Oh, sorry, no, that's the wrong one. So I did mess up. It should be the one which I labeled with, apparently I forgot that one. Okay, well, let's finish that anyway, and I'll come back to it a bit later. I should mention, oh, that looks pretty good. Yeah, there's more than one correct answer. Okay, but we only have 11% vote so far.
So this poll is for students. They can participate and give the answer. So it is requested that all students should answer.
Okay. Okay, well, let me continue then with my presentation. You said it should be up 50 seconds, but we've already passed that. Or should I wait? Do you want? We are 23% now.
Should we end the poll?
I would say so, yes.
Yeah, end the poll, please. Yeah.
But it looks pretty good. So, yeah, let me continue with the presentation. So we're talking about a universal quantum computer, which obviously must have a quantum register, which should be a large array of quantum bits. And to get the computation started, we have to initialize the information. That means we have to write the correct information into that quantum register. The next thing we have to do is we have to process the information, which means applying unitary transformation, which are driven by some Hamiltonians, which change during the processing steps. And at the end, we have to read out the final result. So what I'm going to show you basically how we do that with these nitrogen vacancy centers, which I'm going to introduce in a moment. We use then laser pulses to initialize the information, so to enter the initial condition into the quantum register. And at the end, we count photons to extract the information. In between, we will apply gate operations, and I will see how much time I have to discuss that part of it. Let me add one more thing about applications. I mentioned the case that we can use quantum computers to factorize numbers or get square-free parts of numbers, and these are important if you want to crack codes. But I don't know how many of you want to crack codes. But I think one thing which all of you do daily is to process images and movies and information in digital form. And today, most of the information in the internet is, in terms of traffic and in terms of storage, are images and movies. So if we can apply quantum information to image processing, we certainly have a real killer application. And that turns out to be true, and it is actually potentially extremely efficient. A typical image transformation operation is the so-called hard transform, where you see on the right-hand side the decoded image, which is probably familiar to most of you. And on the left-hand side, the encoded image. But encoded means you have to apply the hard transform to it. Now, to apply this transform, you first have to encode the image, and then you have to process it, and finally you have to decode it. That means you have to bring the digital information back to an image. If you do that on a classical computer, say for a 16 megapixel image, you need at least 16 megabits of information if it's a black and white image, and the corresponding more if it's a color image. So that's a lot of information. If you do that on a quantum computer, it turns out you only need the logarithm of these pixels, which turns out to be about 24 qubits. So it's a much smaller system. You can be much faster, and it turns out even some operations can be done with single gate operations, which are pretty complicated in classical systems. So all of these possibilities are driving the so-called second quantum revolution, where technologies are being developed that use quantum mechanics directly. And all over the world, you see these programs popping up. In the European Union, we have this quantum flagship and a number of other programs which are coming up. In Germany, there is Quantum Technologies Initiative by the Federal Ministry of Education and Research. And of course, India has its programs also. Now, this is a lot of activity which actually started maybe 25 years ago with the first demonstrations of quantum information processing. What's changed even more drastically recently is that private industry is coming in. I've shown you the Google system before, and overall the number of private companies which are entering this market has grown explosively over the last decade or so. You see here both in terms of the number of deals that have been closed, as well as in the amount of money which is pouring into the field. So how does that work? I assume you are all familiar with that. Classical system use bits, which can take values of 0 and 1. Quantum systems take quantum bits or qubits, which also encode the values 0 or 1, but they can also be in superpositions, so we can have something like Schrödinger cats. Now, if you want a quantum bits, you need therefore a two-level system, and actually the only natural quantum bit is a spin 1/2. That's the only two-level system that nature provides. And that has been realized more than 20 years ago, that nuclear spins with a spin of 1/2 are very useful quantum bits. And you can, for instance, use a molecule with multiple spins in the same molecule as quantum registers. That gives you your quantum processing. So I hope I have made a convincing case for quantum information processing quantum computers, but apparently still most of the computation is done on classical computers. And the question is, why is that? Why don't we use quantum computers for everything? Well, there are a number of reasons, but some are that control fields that we have to apply have finite precision, and so we create errors. The other reason is that algorithms always assume that you have an ideal quantum bit or qubit. Unfortunately, such qubits don't exist, such ideal qubits. In reality, they all couple to some environment, which we call bath, and that coupling to the environment leads to the decay of the quantum coherence. We may still have a qubit left, but certainly not an ideal qubit. And in the following, I would like to show you how we try to address these issues in this specific.
But square cut or pear shape, these rocks don't lose their shape. Diamonds are a girl's best friend.
So yes, we like to use diamonds, and you don't have to be a girl to do that. Diamonds are certainly nice to look at, although they are a bit boring. I mean, if you look into diamonds, all you see is carbon in a very regular lattice, and it's not really all that useful in that sense. What we really want is a diamond which has a defect, and in particular, we're interested in the nitrogen vacancy defect, where 2 carbon atoms are missing. One has been replaced by a nitrogen atom, and adjacent to it, we have a vacancy, and together they form the nitrogen vacancy center. And in general, it's these defects or color centers which make diamond interesting and valuable. If you take this nitrogen vacancy center, you have actually 5 electrons in the system, and these 5 electrons together form a spin 1/2. You can identify that center by its fluorescence spectrum, which you see here. That's the blue curve of the NV0 state. We don't really work with this. We work with the negatively charged nitrogen vacancy center, which has an additional electron. So we have 6 electrons, and together they have a spin 1. And to work with that, we then use so-called confocal microscope, where we irradiate the system with a green laser. Through a microscope objective, it focuses the light as close as possible to the center. The center then emits fluorescence, which is shifted to longer wavelengths, And so it is transmitted through this so-called dichroic mirror. That mirror reflects green light, but transmits red light. And we focus it onto a pinhole. And behind that pinhole, we have a detector. This is a so-called confocal microscope, which gives you a pretty good resolution close to the diffraction limit. You see here a scanned image of a diamond crystal, and these yellow dots that you see correspond to NV centers. It's a very nice and stable system. And if you zoom in into one of these yellow dots, you see something like this. And that is for sure a nitrogen vacancy center. But what we cannot be sure from the optical image is if it's a single center. When you see the dimensions that we have here on the diameter of this spot is about 250 nanometer, which is the diffraction limit of the microscope. So in 250 nanometer, you can put millions of NV centers. So you cannot be sure that it's a single one, but that's essential for this type of experiments. To be sure that we have a single center, we do so-called an anti-bunching experiment. That is, we measure the arrival time of the photons, and it turns out if it's a single center, it's almost impossible to get two photons immediately after each other. That's easy to understand. If an atom has emitted a photon, it is in the ground state and it has no energy to emit the second photon. That's why you have this dip at zero delay, and the time it takes to get normal emission again is just how long it takes for the atom to absorb another photon from the laser. So that's the first part, and then we have to look at the electronic structure of the center. I said it's a spin-1 system, so the ground state is a spin-1 and the excited state is a spin-1. Between the two states, we have an energy difference of about 1.9 electron volt. The green laser that we use for excitation has about 2.2 electron volts. So we actually excite the system above the electronically excited state, but it quickly relaxes into that. Now that excitation process is spin conserving. So if the system is originally in the MS equals 0 state, it will stay there. And from the MS equals 0 state, it drops back down in the MS equals 0 state, and almost nothing has happened. It's a bit different if we start in the MS equal plus or minus 1 state. We also bring it into excited MS equal plus or minus 1 state, but then something else can happen. While the system is originally a triplet state, it can cross over into the singlet manifold, and from there it drops down and eventually can end up in either of the two ground states, and often enough it will end up in the MS equals 0 state. And so if you repeat that cycle many times, then you populate the system into the MS equals 0 state completely. So that means we use the laser here to initialize the system into the MS equals 0 state. And that was the first part of the question that you just solved. There's another point here. When the system crosses through the singlet state, you don't get the photon out, and this takes more time. And that means if the electron is initially in the MS equal plus or minus 1 state, it emits fewer photons during a given time than in the MS equals 0 state. And so we can count photons to measure the spin state. So we read out the system by the fluorescence. So let's look again at sort of in a summary. We have an initialization process because the laser puts the system, which is initially unpolarized. So all the 3 spin states have equal probability, but then we use the laser to bring it almost completely into the MS equals 0 state. So that's the initialization part. We also use the laser for detecting the spin. And as I mentioned, because of the intersystem crossing, the fluorescence rate depends on the spin state. The maximum amount of photons that we can get out of a single spin center is about 100,000 photons per second. And so if we measure, for instance, 1 millisecond, we will get on average 100 photons because of the Poissonian distribution. This is a bell-shaped curve like the one shown here. If instead we start in the ms equal plus or minus 1 state, we only get about 70 photons out on average, again with a certain distribution. And so you have to set your limit somewhere, maybe about here. If you get more photons, you decide the system was in the ms equal 0 state. Below it, it was in the ms equal plus or minus 1 state. So this is the readout part, which was the second part of the poll, where you see that the laser can be used for detection. So this summarizes again the quiz. Was the question, can we use lasers to initialize the spin state, to read the spin state, or to find the spin centers in the crystal, or create defects? And the correct answers were, use it to initialize the spin state, and we use it to read out the spin state, and to find the centers. That was this microscope image that I showed before. Now, let's look at the processing a little bit in terms of magnetic resonance. What we basically do here is electron spin resonance or electron paramagnetic resonance on single spins. And we have this S equal 1 electron spin. And if we count photons, we can determine the energy difference between them just by scanning a microwave field across the resonance. And when the microwave frequency matches the energy separation between the two, then we know we are at resonance, and we have measured the splitting between the ms equals 0 and the plus and minus 1 state. This is how the system looks like in the in zero magnetic field. We have only the so-called zero field splitting of 2.87 gigahertz. If we apply a magnetic field, then we get the Zeeman shift of the plus and minus 1 states, and the resonance line splits into two, and these are the two red lines. So what this shows is that this energy level diagram has some handles with which we can work. We have the zero field splitting called D, and it turns out that this D depends on temperature, just because the crystal expands when you heat it. And we have the Zeeman splitting, which depends on the magnetic field. And this is a possible source of or possible handle that we can use for sensing. We can measure the transition frequencies, and that gives us a sensor of the size of a single atom. And we can use that, for instance, to measure temperature. This shows how the frequency varies with the external temperature. Here, over a range of about 100 millikelvin, you get a clear shift of the frequency. And there are other possible effects that you can measure with these very small sensors. Temperature is one example. You can measure magnetic fields. I'll show you that in a moment. You can also measure electric fields, or you can measure pressure, or there are more possibilities than I can discuss here. So let me go back to the issue of quantum computing, and here we come to the next quiz. I'm actually not sure if I gave you this list of questions also, but we'll see in a moment. So what are the required steps in quantum information processing in the network architecture? Possible answers: what is the network architecture? What is the, or can you, or do we need to do an initialization of the quantum register? Do we need to do quantum error correction? Do we need to do readout? Do we need to do processing? Or do you have to generate entanglement? Now, I hope I did send you this quiz. Yeah, that will, so apparently this was labeled with number 43. Yeah, and we have that. And the poll is running. This is more for me as a feedback to see, say, if what I can count on in the background knowledge of the audience.
Should we end the poll?
I guess we can, sorry. Sure. I guess we can end the poll. Yeah, that's interesting. So let me show you my answers. And maybe you won't agree on all of that. So no, but this, what is the network architecture? I forgot to add in the poll, so we won't have that. That was not meant to be a right answer. Anyway, it was my idea to find out if somebody does not know what it is. Anyway, we need initialization. I guess most people chose that, and I just discussed that. We don't really need quantum error correction. If you have an ideal quantum computer, you don't need quantum error correction. However, in any practical quantum computer, which does something really useful, we will need quantum error correction. So maybe I could give that half a check mark in here. Anyway, we certainly need readout. If you don't have readout, you will never find out what your computation would have given you as a result. You obviously need processing to generate, to implement the algorithm. And we actually don't need to generate entanglement. We can discuss that point separately in the discussion section if you like, but that's not on my list. Anyway, this is again the concept I introduced before, and I would like to show now how this is implemented in the system that I was discussing. So let's start with the gate. I already discussed the initialization and the readout part. Let's go to the gate operations. And first, I will discuss the electron spin. The electron spin is the easier one, and that's the one that we always need. So I start with that one. I mentioned initialization, so we apply a laser pulse to bring the electron spin into the ms=0 state. And then we can apply a microwave pulse to implement the gate operation. So that microwave pulse is normally resonant with one of the transitions in this system, maybe also with both of them, that depends. And then we do a readout operation. So the readout tells us in which state the system is after the gate operation. And the typical result looks like this. I'm just showing the count rate, the measured count rate on a relative scale. And when you reach the minimum, you know that the system is in the ms=1 state. When you reach the maximum count rate, you know the system is in the ms=0 state. And if you just increase the duration of this gate operation, then you see an oscillation between the 1 and the 0 state, or I should say between the 0 and the 1, because you start in the 0 state. These are called Rabi oscillations, and you can actually continue them for quite some time. I show you here a longer time scale, and you see you get many, many oscillations. You can get hundreds of them actually, and that shows you that the fidelity for such a single qubit gate is pretty high, on the order of 99%, depending on the details of the experiment. So that's a simple type of gate operation. Another operation which is very important is free precession. In free precession you can get by basically splitting this microwave pulse into two. You have a first pulse which creates a superposition of the two basis states. Then you have a free evolution period under the internal Hamiltonian. You have a second pi/2 pulse to read out the result. It converts the coherence into populations, which are then read out by the laser pulse. If you do that, then you increment the delay between the two microwave pulses, you get the signal like the one shown here. This is called either a free induction decay, or it's called Ramsey fringes. Ramsey fringes because it uses the Ramsey method for measuring the free precession. Now, in principle, if it's a single qubit, you would expect that you get a sinusoidal oscillation. You see here we do get an oscillation, but it's certainly not sinusoidal. You have kind of echoes, you have an envelope or a beat signal. And to understand what's going on, it's best to do a Fourier transform from the time domain into the frequency domain. And you see in this case, you get 6 resonance lines. Now, this is a single electron spin and a single transition of the electron spin. So why do we have 6 lines instead of 1? And the basic reason is that in the vicinity of this electron, we also have nuclear spins. In particular, we always have the nitrogen 14, well, sometimes the nitrogen 15, but in our cases, it's always a nitrogen 14. And there is an interaction between them called hyperfine interaction. And because the nitrogen 14 can have 3 different spin states, we get a splitting into 3 resonance lines. In addition, diamond consists of carbon atoms. Most of the carbons, 99% of them, are carbon-12, which don't have a nuclear spin, but every now and then you have a carbon-13, which has a spin 1/2. And so if one of them is close enough, you have another splitting into 2 lines, which gives you these 6 lines together. And this is actually quite useful. That's why I call it a hybrid system. We can use, excuse me, not only an electron spin, but also nuclear spins. And you may have more than one. So for instance, here we get from a single electron spin transition quite a bunch of lines. And the biggest splitting in this case is because of a carbon-13, which has a hyperfine interaction of 8 megahertz. A second one, which has 5.8 megahertz. I already mentioned the nitrogen 14, which has a splitting of about 2.2 megahertz. And here another carbon-13, which has an interaction of 0.4 megahertz. So that's why I call it a hybrid system. We have an electron spin and we have one or multiple nuclear spins. And that brings some useful properties. It brings also some challenges. First of all, we have the electron spin, which is essential. It's always there, and it's essential for initialization and readout. It's also nice because it has a high coupling strength to microwave fields, so we can get rather fast gate operations on the electron spin. Then we have nuclear spins like the carbon-13. They also have nice properties. They have long dephasing times. We can have many of them depending on the center, but they are a bit sluggish. They don't interact so well with the external control field. So I come here to the next quiz. What are the typical frequencies for spins in a magnetic field of 0.1 Tesla? So question is, how much do you know about magnetic resonance, basically? So 100 millitesla, how much does that give you for the electron Larmor frequency, for instance? Is it 30 gigahertz for the electron spin and 1 gigahertz for the nuclei? Is it 3 gigahertz for the electron spin and 1 megahertz for the nuclei? 10 megahertz for the electron, 100 kilohertz for the nuclei, or 1 gigahertz for the electron and 10 megahertz for the nuclei? And in this case, there's only a single correct answer, as you can imagine.
Participant, you can answer, you can select your option from the poll, so please be attentive.
By the way, we don't know who votes what, so if you got the wrong answer, we can't blame you. Well, we can probably close the poll. We have a winner, and it's nicely the right one. I mean, the Larmor frequency of the electron is determined by the gyromagnetic ratio of the electron spin, which is 28 gigahertz per Tesla. So at 0.1 Tesla, you get about 3 gigahertz. So the correct answer is this one. These are just orders of magnitude, and it doesn't matter too much in detail. But the important point is that the interaction strength for the electron is about 3 orders of magnitude larger than for the nuclei. And that is really important, and you will see in a moment why. So that shows us also in which frequency range we have to expect the transitions. We want to drive electron spins and we want to drive nuclear spins. And so if you look at the system, we have these transitions at 2.87 gigahertz plus or minus the Larmor frequency. So the electron spin resonance transitions are clustered around this 2.87 gigahertz, so close to 3 gigahertz. This is in the low field limit, where the Zeeman interaction is small compared to the zero field spin. And then we have nuclear spin transitions. They happen, pure nuclear spin transitions happen at constant electron spin levels. So they are inside, for instance, the ms equals 0 multiplet, or the ms equal plus and minus 1 multiplet. And they are determined by a change by 1 quantum in the nuclear spin quantums. So these frequencies are close here to 0 gigahertz, or say in the megahertz range anyway. Actually, this range is even narrower than I show here. So, yeah, if you want to read up more, this is a reference on specific of magnetic resonance in the nitrogen vacancy set. There are exceptions, but I certainly won't have time to go into that during this talk. So anyway, as I mentioned, there is a big difference in the interaction strength in these hybrid systems. We have strong interactions for the electron spin and weak interactions for the nuclear spins. So for instance, Rabi frequencies of the electron spin are on the order of 10 megahertz, while Rabi frequencies of the nuclear spins are 10 kilohertz if you're lucky, and less if you're not so lucky. So at the same time, the dephasing times for these spins or qubits differ vastly, again by about 3 orders of magnitude. The typical dephasing time for the electron spin is on the order of 10 microseconds, and for the nuclear spins on the order of 10 milliseconds. So this poses some challenges, and if I have enough time, I can show you how to deal with that. But let's start with a typical experiment. We have now, say, a 2-qubit system where we use an electron and 1 nucleus, and we again have to initialize the system. So as I discussed, you apply a laser pulse to bring the electron spin into the ms=0 state. The electron spin, the laser polarizes the electron spin, but it does not affect the state of the nuclear spin to first degree. So the nuclear spin is completely depolarized after that, and that means you cannot use it as a qubit. You first have to polarize it. And this can be done by applying, first of all, a microwave pulse on one of the 2 transitions to excite the electron spin, while it leaves the nuclear spin unchanged. And then you apply a radio frequency pulse to excite the nuclear spin while leaving the electron spin unchanged. What you have now is that the nuclear spin is completely polarized. The price that you pay is that the electron spin is completely depolarized. Both electron spin states have equal population. So what did you gain? Well, what you can do now is you apply another laser pulse. As we know, the laser pulse polarizes the electron spin and leaves the nuclear spin unchanged. So you can now have a fully polarized system. And with that, you can now apply gate operations to the nuclear spin. Here, for instance, by a radio frequency pulse on the carbon-13, and you see again Rabi oscillations. You can also do free precession experiments on the carbon-13, so you measure free induction decay. And as I mentioned, these are the relevant interaction parameters. You have a gyromagnetic ratio of the electron of 28 gigahertz per Tesla, on the carbon 10 megahertz per Tesla, on the nitrogen 3 megahertz per Tesla. And you have interactions between them. So what do we do now if you apply gates for the nuclear spin? I already mentioned that you can apply a radio frequency pulse. In the case I showed, it was a pulse on the carbon spin, but of course you can also do that on the nitrogen spin. Well, you have to be able to control your system. That's possible by choosing the right frequency, pulse duration, phase, and so on. Addressing is not so much of a problem, but precision can become a problem. And the main problem that we have in this case is the duration. These radio frequency pulses just last too long. Okay, I have here another quiz, but maybe we should skip that because I only have 5 minutes left. And so I will directly give you the solution. I asked what are the required operations that you need. Okay, the poll is already up, so you can answer if you like. And I just won't wait very long. So you certainly do need arbitrary rotations of single qubits. You certainly need a controlled NOT operation. Well, the Toffoli gate is useful, but you don't need, but yeah, thank you. The controlled NOT gate is essentially, Toffoli gate is useful, but you can decompose it into controlled NOT operations, so it's not essential. Thanks for the pulse. So yes, I mentioned you can drive the nuclear spins by applying radio frequency pulses. Here the example, the nitrogen-14. And in the case of the nitrogen-14, you have basically 6 relevant transitions. You can address them by choosing the right frequency. Here, for instance, you see an example of a Rabi oscillation at 2.8 megahertz, which corresponds to one of the transitions, the second one at 4.9, and the third one at 7 megahertz. So that shows that we have universal control. Well, it shows part of it, but I can assure you the rest also by applying radio frequency fields. However, there is a problem, or at least 2 problems. And those I would like to show you before I end. They become apparent if we do a 2-qubit gate. 2-qubit gate requires you, as every operation, first an excitation laser pulse to polarize the system. Then you apply, for instance, a microwave pulse on the electron spin transition to create this coherent superposition or to polarize the nuclear spin or both. And then you apply your radio frequency pulse to the nuclear spin. This radio frequency pulse you can easily calculate if you have, for instance, 10 kilohertz Rabi frequency, can last, say, 100 microseconds. The problem is, during these 100 microseconds, you completely lose the coherence that you have created in the electron spin. So if you expect to see a Rabi oscillation as a function of this radio frequency pulse, the actual measured signal is shown here by this black curve, is just a decay. Because during 100 microseconds, the electron spin coherence decays normally. I mean, we know that sometimes we can recall coherence, and the earliest such experiments are the spin echoes by Erwin Hahn, measured in nuclear magnetic resonance. You create a coherence, you let it decay, and then you apply a so-called refocusing pulse, which inverts the interaction between the system and environment. And what it does is shown here in this cartoon. You have runners on a track which run at different speeds, so they get apart. But when you let them run backwards at the same speed, then they come back into phase. So at the end of the race, they are all cross the finish line at the same time. And that's what creates this echo. So this is a refocusing experiment which can be done on nuclear spins, but also on any other 2-level system or more complicated system. So you can have photon echoes, you can make them on charged qubits and so on. And we can, of course, apply such echoes in the NV center. So what we have to do is to refocus the electron spin coherence. In this case, we do that by applying 2 refocusing pulses in a gap that we leave in the radio frequency pulse. That's a so-called protected 2-qubit gate or protected CNOT. And if you do that, you actually get the coherence back, and you get a signal which is pretty close to the expected signal of the system. So I see that I'm nearing the end of my time. So let me skip a few slides and come to the conclusions. what I tried to show you. Yes. Okay, what I've tried to show you is that we have here nuclear and electron spins. Part I had to skip, which is that sometimes the nucleus and the electron interact in such a way that you get qubits which are really hybrid, so they have properties of nuclei and electrons. These hybrid systems are very useful for some applications, but they also pose challenges. I also had to skip the part of the indirect control. So it turns out we can avoid some of the problems by these radio frequency pulses by just omitting them and doing what we call indirect control. And never forget, diamonds are our best friends. Thank you for your attention.
Okay, thank you, Professor Suter. Thank you very much. I'm sure the students enjoyed it very much. So now we have a question and answer session. There are a few questions which have been typed in the chat box. I can read them out for you. Okay. So first question is, could explain anti-bunching and its link to production of single photons a bit more detail, in a bit more detail.
Okay. So let me get back to the slide.
Yeah, you can.
And share the screen again. Yes, so this is, it's an interesting experiment, by the way. It was originally brought up in astronomy to identify or to characterize light from very distant stars, but it's most useful for classifying sources of light. And as the person mentioned correctly, it's a way to make sure that you have single photons. So an atom or such an atomic center is basically a single photon source, because when it has emitted a photon, it's in the ground state, so it has no energy left to emit a second photon immediately afterwards. And this is what you measure when you do the statistics of the arrival time. So zero delay here means that you have just detected a photon and you note the probability that you detect a second photon. For single centers, you have this anti-bunching effect. If you have a classical light source, you actually have a higher probability. And on this scale, it would be 2 in the extreme case, because classical sources, like thermal sources, they have a bunching tendency. The photons like to stick together because they are bosons, so they like to be in the same quantum state. I'm not sure if that fully answers the question, but it's probably as far as I can go with in this context.
Okay, so we can move on to the next question, which is, why can't we use laser to pump it to any arbitrary states, then use filters to filter out only a particular wavelength photons?
Well, what you mean with any arbitrary state?
Yeah, that is the thing.
Moment, wait, I cannot see the chat, but maybe.
Well, maybe you can show the energy level diagram, it will become clear, because there are no arbitrary states, they're just the excited state and then...
Yeah, well, there are of course more states than the ones that I've shown, but so, yeah, I mean, obviously every energy level scheme is a partial scheme. An atom and a center have infinitely many states, but in a way we do that. I mean, we don't use a laser which is resonant with this transition. And there are a number of reasons for that. One is that it makes it easier to distinguish scattered light. So the green light we don't want to have on our detectors. And this is very important because you have so many green photons in the setup, you really have to take care of separating them from the fluorescence light. Otherwise, you would actually destroy the detectors. And that is obviously much easier if you use a different wavelengths to separate it. But can you repeat the question again? I guess I'm getting distracted.
Oh, yeah. Question was, why can't we use laser to pump it to any arbitrary state, then use filters to filter out only a particular wavelength photon?
Yeah, well, in principle, I guess you can do that. I mean, you have to have an allowed transition, of course.
Yes.
If you want to pump it. Yeah, I'm not sure if the person who asked the question wants to specify, maybe you can take the mic.
Yeah, Abhishek, you can unmute and speak.
Sir, if we want single photons, then why can't we just filter out the unwanted ones and choose that particular wavelength? Let's say that particular wavelength was a forbidden transition or a very rare transition. So you can just like assume that it happens very rarely. You can get only a single photon at a time, filter rest of it.
Oh, you're talking now about single photon specific. So it's not so much about this aspect here. Well, you can, of course, extract single photons from the laser. The problem is always you have a finite probability of getting 2 photons or 3 if you just attenuate the laser. And that's not, depending on the context, that probability can be made low enough. But for some applications, you have to be sure. And for that, you need these real single photon sources. So for a laser, you get neither bunching nor anti-bunching. So you don't get that dip at 0 delay. And that means the probability of getting 2 photons in any given window may be too high for your specific application. But there are many applications where attenuated laser beams are good enough.
Thanks. So the next question, again, Abhishek only asked all the questions. So is a direct excitation to nuclear spin forbidden?
A direct excitation, well, that's what you do with the radio frequency pulse. I mean, so the So the direct excitation, which is the one that I've shown you in the case of carbon-13 or N14, was within these multiplets here, within the ms equal plus or minus 1 multiplet, or within the ms equal 0 multiplet. So the electron spin stays invariant, but the nuclear spin changes by delta m equal plus or minus 1. And that you can excite with a radio frequency pulse. You can also, in certain conditions, and that's in the part which I had to skip, excite these transitions with microwave fields. And that happens when there is enough coupling between the electron and the nucleus. And now maybe I better start with this one. So if you put yourself in the position of a carbon-13, that carbon-13, or could be the N14, but let's take the carbon-13. The carbon-13 is the nuclear spin, so it's a magnetic dipole, and that magnetic dipole precesses around the effective magnetic field that it sees. And that magnetic field has two components to it. One is the externally applied magnetic field. And so you get Larmor frequency, which is gamma times B. Now, in the NV system, you have a second interaction, which is the hyperfine interaction. And the hyperfine interaction is anisotropic. That means it has components in very different direction depending on the position of the nucleus. And so that hyperfine interaction will in general not be parallel to the external magnetic field, but it adds like a vector to the Larmor field. And if the electron spin changes here from the ms equal +1 to the -1 state, then this hyperfine interaction inverts. You have the sign change, which changed the sign of the hyperfine interaction. And that means that the effective field also changes direction. So the quantization axis of the nuclear spin depends on the state of the electron spin. Now, if we have a single electron spin, I only take it as spin 1/2 here, and the associated nuclear spin, that means depending on the state of the electron spin, the quantization axis of the nuclear spin, that's the blue here, has a different direction than in the other case. Now, a normal allowed NMR or EPR transition, so nuclear spin or electron spin transition, changes only the state of the electron or the nuclear spin. So you can flip the electron spin, for instance, so the red spin, where the nuclear spin should stay invariant. Obviously, this doesn't work here. If you split the electron spin here from the top left, you end up in the bottom left, but the nuclear spin has a different direction. And that means that the electron spin transitions here, or the nominal electron spin transitions here, don't happen just as pure electron spin transitions. They are combined flips of electronic and nuclear spins. And you see that actually in the spectrum, basically all the possible transitions become allowed, and you get more transitions than you would normally have. So you can excite nuclear spin transitions by microwave pulses.
Yeah, the next question is, how does dephasing of electron spin occur when nuclear spin is excited?
Yes, there are multiple contributions to the dephasing of the electron spin. The biggest in diamond is because of the interaction with many carbon-13s. So you have very many carbon-13s. Each of them has a hyperfine interaction, which by itself is quite small. But when you have 1,000 carbon-13s, each of them with a small interaction, it's like a noisy environment, and that dephases the electron spin. Now, to some degree, this background of carbon-13 hyperfine interactions is static. The electron spin moves much faster than the carbon-13, but each time you repeat the experiment, the environment has changed, and so every time you see a somewhat different environment, and so the precession frequency of the electron changes. Also, when you start the precession of the electron spin, you apply a pulse, so you change the electron spin, and because of the hyperfine interaction, the nuclei notice that change. And so you start to excite the nuclear spins, and they wiggle around, and that again creates a back effect on the electron spin, which contributes to the dephasing.
Well, are there any questions? People can just unmute and ask if anybody. We have something like 10-15 minutes left.
There are other interactions like the zero field splitting, which couples to phonons, for instance, but these are usually much smaller than the effect of the nuclear spins.
Okay, if there are no further questions, let us thank Professor Suter for a wonderful talk, illuminating talk, which everybody has enjoyed and learned a lot of things. Thank you, Professor Suter. So let's unmute and clap.
Yeah, thank you, Data.
Yeah.
Hope to see you in person soon.
Yes.
That would be nice, yes.
Maybe next year, Professor Suter. You keep coming to India, so you can come here.
I will, sure, yes.
Okay.
Yes.
Our first CSIR conference,
yes,
Ahmedabad PRL, and that is where Professor Suter came.
Yeah.
That was quite some time back, you know.
The last time Professor Suter told me he had something like altogether 8 Indian postdocs, right? Maybe now more.
Probably, yeah. Yeah, and most of them have gone back to India, so okay.
Yeah.
Thank you.
Thank you very much.
Bye-bye.
Okay. Yeah. Bye. Okay.
Very nice.